Today we will be discussing the hydroboration of alkenes mechanism, but first let's discuss our reagent.
BH3 is the reactive species in this reaction. It is highly unstable because boron does not have an octet. In its pure form, it exists as a gaseous dimer, diborane.
The two hydrogen atoms are involved in 3 center 2-electron bonds indicated by the orange arrows. These provide stability to the boron atom, but diborane is extremely toxic and explosive.
Therefore, a more stable and commercially sold variation of BH3 is a 1-to-1 complex with THF, where THF acts as a Lewis base to give the boron atom its octet.
The twist with BH3 is that the hydrogen bears a partial negative charge. In this scenario, hydrogen is more electronegative than boron, giving boron the partial positive charge.
The alkene will first undergo hydroboration. It is driven by the flow of electrons from the electron-rich pi bond to the electron-poor boron atom of BH3. This reaction avoids the formation of a highly unstable carbocation by simultaneously forming a bond back to the second carbon atom of the double bond, indicated by the pink arrow. Hydroboration is regioselective, meaning that BH2 adds to the less sterically hindered carbon and hydrogen adds to the more sterically hindered carbon of the C double bond C bond. Overall, 2 bonds are broken and 2 bonds are formed in a concerted fashion, that is, without the formation of intermediates. Next, the product is oxidized with a basic solution of hydrogen peroxide, H2O2. Step 1 is the deprotonation of hydrogen peroxide, indicated by the green arrows.
The coordination of hydrogen peroxide occurs when a lone pair on the negatively charged oxygen attacks the boron atom, indicated by the pink arrow. A 1,2 alkyl shift occurs when the carbon-boron bond shifts to form a bond between the carbon and oxygen, in turn kicking off the alcohol group, indicated by the green arrows. The hydroxide leaving group attacks the boron atom in a coordination step. The bond between the boron and oxygen break, ultimately forming a negative charge on the oxygen. The negative species undergoes a proton transfer with hydrogen peroxide. Ultimately, this forms a syn alcohol with an enantiomer. The hydrogen and oxygen add with syn stereochemistry and anti-Markovnikov regiochemistry.
We hope this enhances your understanding of the hydroboration oxidation mechanism.